In this video, we're going to be talking about bond energy and what happens to bond energy in endothermic reactions and exothermic reactions, as well as we're going to go over the different ways to communicate enthalpy changes in chemical reactions. So when we break chemical bonds, that is a process that requires energy. So breaking chemical bonds is an endothermic process because it requires energy. So remember that endo kind of sounds like enter, so energy has to enter the molecule in order for the chemical bonds to be broken. Meanwhile, forming bonds is going to be an exothermic process because it releases energy. Again, remember that exo kind of sounds like exit, so energy is exiting the molecule when bonds are being formed. Now, when more energy is absorbed to break bonds than is released when forming new bonds, the overall change is going to be endothermic, so that's where we get those endothermic reactions. And when more energy is released forming new bonds than is required to break existing bonds, the overall change is exothermic. So that's how you get your exothermic reactions. Okay, so in the diagram below here, we have it just explaining the endothermic process of bonds breaking and then the exothermic process of bonds being formed. Okay. So in this first part here, we have our molecule plus energy, and then the energy is required to break the bonds, which is that endothermic process I was talking about. Okay, so let's just write that as a note. So energy is being gained. And we know energy is being gained because it's on the reactant side. Okay, so therefore, this is going to be an endothermic process. So I'm going to abbreviate therefore to those 3 dots. Okay, so whenever you have an endothermic process or an endothermic reaction, energy is always going to be on the reactant side. Okay, so now that we have our bonds broken, okay, we have a pile of separate atoms. Now in the second part, in order to form bonds, energy needs to be released. Now, this is showing energy being released because energy is a product, so energy is being produced from this system. Okay, and when your energy is a product, it is going to be lost. So, energy is lost. How we know it's being lost is because it's a product. Okay, so exothermic processes or exothermic reactions, they're always going to have energy on the product side because energy is being produced, it's being released from the system. All right, now let's do some diagrams about endothermic and exothermic reactions. We'll have to scooch them over here. So let's draw a very basic potential energy diagram. So I got my y-axis, my x-axis. This will be reaction progress. Okay, which is sometimes just referred to as time. Okay, and my y-axis is going to be my enthalpy change, which is either it could be in the units kilojoules or joules. Okay. And so how I'll draw this for an endothermic process, so remember, overall we're gaining more energy that is being lost in an endothermic reaction. So let's pretend that's a straight line. There we go. Okay, so here I have my reactants. Here I have my products. So what's happening here at this point is that we're gaining a whole lot of energy in order to break the bonds. Meanwhile, this little section here is just representing that a little energy does get released when new bonds are formed in an endothermic reaction. Okay, so I guess I'll have to put my title for this graph. I'll have to put it down below, unfortunately, because I ran out of room at the top. So this is an endothermic reaction. Okay, now for endothermic reactions, the products are always going to have more potential energy than the reactants. Okay, and because we're gaining energy, your change in enthalpy will always be positive for a endothermic process. So the energy difference or the enthalpy difference between your reactants and products is always going to be a positive value for an endothermic reaction. Okay. Now, let's draw an exothermic reaction over on this other side here. So this time I'll put my title up above. Alright, so let's label our axes. So change in enthalpy in kilojoules, reaction progress, which is also known as time. So I have my reactants. So this is just the reactant plateau, and then we'll do my product plateau. So keep in mind, I'm just using the words reactant and products just because this is a general exothermic reaction. If I knew exactly what the reaction was, I would be putting exactly what the reactants are, exactly what the products are. Okay. So in this exothermic reaction, we have a little bit of energy is being gained in order to break the bonds. So I guess you could say a little bit of energy is being absorbed by the system. Same thing. A little bit of energy is absorbed to break bonds. Okay, and meanwhile on the other side we have a lot of energy being released in order to form new bonds. Actually, before we move on, just going to add in here. So for exothermic reactions, your change in enthalpy is always going to be negative for exothermic reactions. Okay, so notice here for exothermic reactions, your products are always going to have less energy than your reactants. Okay, so you should know the general shapes of both exothermic potential energy diagrams and endothermic potential energy diagrams. All right, now there's 4 different ways to communicate enthalpy change. You need to be able to do all of them. So molar enthalpy, enthalpy change, thermochemical equations, and potential energy diagrams. So you need to be able to calculate molar enthalpy and enthalpy change. You need to be able to write thermochemical equations and draw potential energy diagrams. Okay, so molar enthalpy, what that is the enthalpy change that occurs for 1 mole of that substance. Okay, so the key thing here is that molar enthalpy is specifically for 1 substance. Okay, so meanwhile, compared to enthalpy changes are for the entire reaction. Okay, so that's the difference between the two. All right, going back to molar enthalpy here. So molar enthalpies can be used to communicate exothermic or endothermic changes. The symbol for molar enthalpy is delta H, often with some sort of subscript to indicate the type of change. Okay, so let's do this off to the side here. So for molar enthalpies, here's the different types of subscripts you'd be expected to know. So for the molar enthalpy of formation, that'd be delta with a subscript F and then H. So F is for a formation reaction. If you have delta with a subscript D, H, that is the molar enthalpy of decomposition. And then delta subscript C, H. The C is for combustion. So this is the molar enthalpy of combustion of some specific substance. Okay, so the subscript letters, they're just specifying what type of reaction is happening. Okay, now if you wanted like a very general variable for molar enthalpy, you could say delta subscript RH. The R just means reaction, so this would read as the molar enthalpy of reaction for some substance. Okay. All right, Now, enthalpy change depends on the number of moles of a reactant and product in a chemical reaction. So, for example, the molar enthalpy of reaction on 2 moles of a substance would be double that for 1 mole. Now, as I said before, exothermic reactions have a negative change in enthalpy, and endothermic reactions have a positive change in enthalpy. Okay, so that's something you really need to know. The formula, change in enthalpy is equal to moles times the molar enthalpy of reaction, is used to determine enthalpy change. Okay, so for example, for what we talked about earlier here, where the molar enthalpy of reaction on 2 moles of a substance would be double that for 1 mole. So look in here, okay? So we have this reaction where sulfur dioxide is reacting with oxygen to create sulfur trioxide, and the change in enthalpy for this reaction is negative 98.9. Now in the second reaction, we're doubling everything, or the amounts of everything in the reaction. So then it would make sense that the change in enthalpy, since we have double the amount of substances, both reactants and products, we're going to have double the amount of change in enthalpy. So I'd go negative 98.9 multiplied by 2. So this 2 is coming from the fact that we took this equation and we multiplied everything by 2. So that's going to give us negative 197.8 kilojoules. All right, now on to thermochemical equations. So if a reaction is exothermic, just like the one above, it's going to be releasing energy. So that's why our energy term is negative, because energy is being released. Okay. So in order to turn it into a thermochemical equation from what we've been given, so anytime you see a change in enthalpy written like this is called like delta H notation or enthalpy notation. Sorry, change in enthalpy notation. Okay. So if we have an exothermic reaction, energy is being released from the reaction, therefore it's going to be a product. Okay, so if a reaction is exothermic, it releases energy, so the energy term will be on the product side. And also, whenever you write your energy term, even though it was negative 98.9, we still put a plus to say that this is an additional product here, or energy is an additional product. Okay, so the reason why we put a plus sign and not a negative sign is that the negative sign is already taken into account by the energy term being on the product side. Similarly, if a reaction is endothermic, it requires energy. So you can write the amount of energy it needs right into the equation on the reactant side. Okay, so again, here's our energy term. It's on the reactant side. That means energy is being gained by your system. All right, so both of these here that we just talked about, both of those are thermochemical equations. So what a thermochemical equation is just a reaction that has an energy term in it. That's what it is. Okay. Now, the units that the energy term is written in are going to be in kilojoules and not kilojoules per mole. Okay, so kilojoules, that's a change in enthalpy, whereas kilojoules per mole is molar enthalpy. So molar enthalpy only talks about one specific substance in the reaction, whereas change in enthalpy is going to talk about the energy changes happening in the reaction as a whole. Okay? So energy is either going to be a product if you're talking about an exothermic reaction, or a reactant if you're talking about an endothermic reaction. Okay? And once again, when you're writing the energy term in your reaction, you never write it as negative. The negative will be taken into account by being on the product side if your change in enthalpy is negative. Okay? If your change in enthalpy is positive, you write it on the reactant side. Okay, so change in enthalpy in the equation is not the same as an experimental change in enthalpy. So what this is saying is if you get a point of data for change in enthalpy, okay, it's going to be a little bit different than experimental change in enthalpy. All right, standard enthalpies of formation. These can be found on page 4 and 5 of your data booklet. So if we look here, go to page 4 and 5. These are the standard molar enthalpies of formation. So here we're given the units that all of these are in. They're all in kilojoules per mole. Okay, and all of these are just the molar enthalpies of formation. If you wanted to find the molar enthalpy of decomposition, all you would do is you would take the sign and flip it. Okay, so looking at aluminum oxide, the molar enthalpy of formation for it is negative 1,675.7 kilojoules per mole. If we wanted the molar enthalpy of decomposition, it would be positive 1,675.7 kilojoules per mole. Okay. All right. So these formation reactions down below here, they're balanced and record values based on 1 mole of the compound here. Okay, so just as a side note here, how these are written with your chemical reaction and then your delta H over here, this is called delta H notation. Okay, so if a question asks you to write a chemical equation and the enthalpy term in delta H notation, this is what it means. However, if your question asks you to write a thermochemical equation, this is what it means. Okay, so both talk about the chemical reaction happening and the energy either being gained by the system or lost by the system, but they just do it in 2 different ways. Okay, so you need to be able to read and understand both ways and be able to write both ways as well. Now, looking at what we're given here, we can tell that this first chemical equation, it has a positive change in enthalpy, which tells us that this is an endothermic reaction. So positive delta H means endothermic reaction. Meanwhile, for the second, since it's a negative change in enthalpy, that tells us that it's an exothermic reaction. Okay, so the change in enthalpy just talks about energy being either absorbed or released. And we're just going to cross this last part off because if it was a per mole basis, that would be molar enthalpy. So make sure you cross that off. Okay. So again, main distinguisher between thermochemical equations and change in enthalpy notation is that for thermochemical equation, the energy term is written right into the chemical equation, whereas for delta H notation or change in enthalpy notation, the change in enthalpy is written separate from the chemical reaction. So you do need to know the difference between the two. All right, so keep in mind with enthalpy changes, it really does make a difference with what states your substances are in. So for example, if we look at the formation of water as a liquid, our change in enthalpy is going to be negative 285.8 kilojoules. But if we look at the formation of water vapor, so water as a gas, notice that we have a different change in enthalpy. Now it's negative 241.8 kilojoules. Okay, so there's a little bit less energy released when we are forming water vapor. So essentially, be very careful with states. Make sure you pay attention to them. Now, molar enthalpies are given for compounds only. The molar enthalpy of formation for elements, we're going to be assuming that there's 0 in Chem 30. Okay, so that's important. Anytime you have the formation of elements, you assume, or if you need the molar enthalpy of formation for elements, you're just going to assume it's 0. Okay. Now, visually, what the standard enthalpies of formations would look like would be these two diagrams. So over here on the left, we have the formation of hydrogen iodide gas, okay, which has a positive molar enthalpy. Okay, so that means it's an endothermic reaction. So I'm going to abbreviate endothermic just as endo, so it gains energy. So it makes sense that it's going to be a positive molar enthalpy, okay, because endothermic means that you gain energy. Okay, and what the potential energy diagram would look like for this. So this is a very simplified potential energy diagram, but we still have the reactants labeled. Now that we have an exact chemical reaction to talk about, we still have the products labeled. We still have the X and the Y axis labeled with units, as well as the change in enthalpy. Okay, so those are the key things you'd be looking for if you need to draw a potential energy diagram. Okay, so for endothermic reactions, your products are always going to have more energy than your reactants. Meanwhile, for the formation of water as a liquid, we have a negative molar enthalpy of formation here. So that means because molar enthalpy of formation is negative, it's an exothermic reaction. So I'm going to write exothermic just as exo, which means that energy is exiting the system, so you're losing energy. Which makes sense why this is negative. If we're losing energy, it has to be negative. Okay. And so in an exothermic reaction, your reactants are going to have more energy, more potential energy than your products. All right, so important notes. All molar enthalpies of formations for elements are going to be 0, so that's super important. Most values are negative for molar enthalpy of formation, and in reality, all exothermic reactions do have activation energy, and this energy requirement prevents a spontaneous reaction from occurring. All right, so first example here, write a thermochemical equation. So that's important wording here, so that tells us that the energy term is right in the reaction. For the formation, so that tells us what type of reaction is happening of water vapor. Okay, so remember, just as a quick review of formation reactions, what the basic idea of them is that you are forming a compound from the elements that make it up. Okay, so if we think about water, H2O, the elements that make it up are hydrogen and oxygen. Okay, so let's start writing this. So hydrogen, which is a diatomic element, which exists as a gas. Okay, so how I know it exists as a gas, if we go to our periodic table and find hydrogen, it's colored blue. And if we look at our key, blue means that it is a gas. Okay, if you're thinking to yourself, diatomic elements, it's been a hot minute since I've taken a chemistry class. What exactly is that? Diatomic element just means whenever it's by itself, there's always 2 atoms of it. Okay, and the diatomic elements, what they are, I like to remember them as Hofbrinkel. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Those are all of the diatomic elements that you need to know. So if any one of these are by themselves, not in a compound, there's always going to be 2 of them. Okay, and that's also assuming that they're not in solution. Okay, so while we're talking about diatomic elements, I'll briefly mention polyatomic elements. So these are elements when by themselves there's more than 2. Okay, so there's only 2 polyatomic elements. That's going to be phosphorus. So when it's by itself, not in a compound, it always exists as P4, and sulfur. So whenever it's by itself, not in a compound, it always exists as S8. Okay, and again, both of these are assuming that it's not in solution. All right, so we have the formation of water vapor. So we're forming water from its elements. So hydrogen, diatomic, oxygen, also diatomic, and if we look at our periodic table, oxygen is blue, so it exists at room temperature as a gas. And since it's water vapor, I'm going to put water as a gas. So it's very important that you have states for all of your substances in a chemical reaction. Okay, now at this point we have a skeleton equation. Now we need to balance it. Okay, so what that means is we need to have the same amount of each element going into the reaction as coming out. So I have 2 atoms of hydrogen going in, 2 coming out. I have 2 atoms of oxygen going in, but only 1 coming out. So I'm going to write, so how you balance a chemical reaction is through the use of coefficients. Coefficients are the big numbers that come in front of each chemical species. Okay, you do not play around with the small subscript numbers in order to balance a chemical reaction. The subscripts are only there to balance ionic compounds. Okay, So I'm going to write a 2. So what that means is now I have 2 oxygens going in, 2 coming out, okay, because a coefficient affects everything in the compound that comes right after it. But now I have 4 hydrogens coming out, but only 2 going in. So I need to write a 2 here. Okay, so now I have 4 hydrogens going in, 4 hydrogens coming out, 2 oxygens going in, 2 coming out. This is balanced. All right. So now we need to be concerned with writing the energy term in here. Okay, so now that we've written our balanced chemical equation, now we need to find the molar enthalpy of formation of water. So let's just write this as steps here. So step 1, write a balanced chemical reaction. Step 2, find the molar enthalpy of formation of, in this case, water. Okay, and we're paying attention to, this is water as a gas, not water as a liquid. Yeah. So let's find that on, it's probably on page 5. Okay, so we've got water as a liquid, water as a vapor, we want vapor. Okay, so that's going to be that negative 241.8. So let's write that out. So change molar enthalpy, or molar enthalpy of formation is equal to negative 241.8, and that's kilojoules per mole. Now, since we want a thermochemical equation, we can't just throw molar enthalpy in there because you only report change in enthalpy in a thermochemical equation. You do not report molar enthalpy. Okay, so we need to look, and this is specifically for water vapor. So let's look and see, okay, how many moles of water vapor do we have? We have 2 moles of water vapor. Okay, so why I'm paying attention to how many moles of water vapor I have is because of this formula. This enthalpy change is equal to moles times molar enthalpy. It's molar enthalpy of reaction, but in this case, we know that this specific reaction is formation, so I'm going to write formation. Okay, so this says in order to find our change in enthalpy, we need to take our moles and multiply it by our molar enthalpy. The reason why we're using our coefficient is because we haven't been given any other additional information that would specifically tell us how many moles of water vapor we have. Okay, so that's why I'm using this. So, actually, what I'm going to do here is I'm going to say step 3, find change in enthalpy using delta H is equal to moles times molar enthalpy of reaction. Okay, which you can specify when you actually know the identity of what type of reaction it is. Okay, so that's what I'm going to do here. So our moles, we have 2 moles of water vapor multiplied by our molar enthalpy of formation for water vapor, which is negative 241.8. Okay, I'm going to write moles in here and this is kilojoules per mole. So that's going to give us negative 483.6 kilojoules because the moles, they're canceling out. Okay. So to write an actual thermochemical equation, I'm going to take that number, and because it's negative, that means put it on the product side. Okay, so I'm not going to write minus 483. I'm going to write plus 483 on the product side because writing it on the product side takes care of the negative. So let's write ourselves a little note. If energy is negative, it goes on the product side. Okay, now if it really bugs you to leave the coefficient for oxygen blank like that, you could always write a 1. Okay, so if there's no number for a coefficient, you can assume that it's 1.